But welcome, guys, to session 8 of the online groundwater mentorship program. Today, we'll go through the groundwater modeling process and compiling your modeling report. This session outline, we'll go through the mentoring schedule going forward. Then we'll go through the types of models that we encounter in groundwater, model applications and selecting your model, then the modeling process itself, just an overview of the general process we follow, and then what we need to include when we are compiling our modeling report. Okay, so here is the schedule. Sorry, I just need to send something quickly here. So today we're doing the modeling. Then the next session on the 27th of August would be groundwater in the mining environment. Then after that, we'll do management and monitoring of groundwater. And then, we'll sort of see what any additional subjects we would like to cover in session 11. Any suggestions for any other topics you guys want covered in this, the mentorship program?
From my side, I think you covered basically everything that I just also needed in the beginning. So I think it's a pretty comprehensive approach.
Great, thanks so much. Yeah, and then what we'll cover in the session 11 or session 9 is sort of end users. That's the different types of groundwater users. I think we'll get a guest speaker in there. Maybe we can get James to chat to us about the water treatment and how groundwater can be adapted for all of the different processes. So thanks for that one, James. Yeah, Antonio, groundwater slope stability. Yep, we'll add that one into the groundwater in mining section. We'll look at slope stability and depressurization. It's a bit more advanced, so we'll just sort of skim it, but we will include that. Okay. Any other suggestions, or can we carry on with the modeling?
Maybe something about dewatering and a little bit more on mining-based dewatering, and also if we can look at base heave and that type of stuff.
Just repeat that last one there, Neil, sorry.
Base heave.
Base heave, oh, okay. No, 100%, we'll put that in this last one then with the groundwater and underground tunnels and that, and we can look at the base heaves and more a construction approach there. That's noted. Great. Anybody else? Notions on quality? Now we'll look at quality of groundwater in this management and monitoring section. Dewatering. James, we've covered this, the safe yield and all of those concepts in a previous session on the sustainable yield. I'll have a chat with you about that one. I'll give you a call or something. Okay, so let's carry on with modeling. I think this is something that a lot of people are interested in. Yeah, so, sorry. Yeah, so the first section, we'll look at the types of model that we get in groundwater modeling. Does anybody have an idea what types of models we deal with typically? Just before we go through it.
There was something in literature about static models and transient models. I will see how you deal with those two, because I just read through quickly, but I think they talked about something about that.
And it will also include analytical and numerical and conceptual models.
There we go. Yeah. Anybody else? So we've got analytical, we've got numerical. Any other types of models that you can think of?
Define element and define difference, or I think that's how you pronounce it.
Oh, the finite element,
Yeah,
finite
the
difference.
finite, yeah.
Yeah, no, that's part of the numerical models. Okay. So let's go through the sort of main three. First one is a physical or a bench scale model. Typically you do this in the lab or it's at university just for educational purposes. I'm sure, I know at Free State they have a bench scale model that Gerrit built. I'm not sure if anybody else has seen one. Yeah, you use a sand tank, membranes or electrical materials to represent the groundwater environment. It's very limited application in the real world because they're cumbersome to build, they can get quite expensive. And also, I mean, the electrical ones are quite complicated. So they can also be misinterpreted. So that's the first kind. Then we have analytical models, which apply relatively simple mathematical equations to solve flow or transport problems, and in terms of controlling or known parameters. The advantages of your analytical models is that you have limited input data requirements. You only need to know one or two elements of your equation to do an analytical model sometimes. When they are applicable to your site, they're the cheapest modeling technique by far. The computational time required is negligible because it's just usually an Excel spreadsheet or something like that. Rough answers are possible with literature values only. So you don't always need site-specific data for an analytical model. The primary disadvantage of an analytical model is that the solutions are often subject to a number of assumptions and limitations, which makes a solution applicable only to ideal cases. If you think about the Cooper-Jacob equations we've gone through, there's quite a list of assumptions and limitations. So you need to think about it carefully before you apply an analytical model. And a good example of an analytical model that you can apply to most sites is Darcy's law. Yeah, just a quick Darcy calculation on your discharge into a box cut or something. It's not going to give you a final answer, but it'll be enough to get you going, to do a sanity check. Okay, so you can, when applicable, you use the analytical models to evaluate the effect of a single parameter on other parameters. So for example, in Darcy's law, you can see how your changes in conductivity will affect the discharge to an area. So if you have a fixed area and a fixed groundwater gradient, you can evaluate what a change in your conductivity if you shotcrete or if you have a blast shatter zone around your tunnel or your pit. You can evaluate that quickly using Darcy's law. Okay, then the other type we use is a numerical model. Numerical model is an idealized representation of some or all of the characteristics of a real-world system on an appropriate scale. It's a mathematical system which is able to approximate the behavior of a real-world system or process, at least partially. And remember, a model is a simplification of reality, where real-world entities are simplified and translated into mathematical entities to be represented by mathematical equations. So that's where your conceptual model is important, because you're translating a real-world thing into a block or into a layer that is all these equations are applied to. And then this is what Neil mentioned. You've got your governing equations solved numerically using either finite element or finite difference codes. So your codes is the finite element, which uses integration to solve the governing groundwater equation. And you have polygons for your cells. Or you get the finite difference code, which uses partial differentiation to solve the groundwater governing equation. I'm not going to go into the maths behind these codes, but the essential main difference is the shape of your grids. So for finite difference, the advantage is that it's you can model on a more intuitive basis. The data entry is quite easy because it's regular grid cell sizes. You just color in your regular grids. The matrix techniques are quite efficient, and then programming is quite easily changed, relatively easily changed. Disadvantages is that it has a low accuracy for some problems because you have regular grids required. And then the software costs, that should be an advantage, sorry. Software costs are lower, which should be an advantage. Yeah, then finite element, your advantages are the flexible grid geometry, so you can fit your grids a lot better to your environment. And you get a high accuracy possible with a finite element model, such as a fee flow model. And evaluates your cross product terms better. But then the disadvantages of finite elements is that it's a complicated mathematical model. The data input is quite difficult. You need more data to get a decent model out of it. The programming is difficult and it's expensive. To compare your license cost for a finite difference, a ModFlow model, your proprietary software, you're looking at between $1,500 and $5,000. Whereas for finite element for fee flow, you're looking at probably about 150 to 200,000 Rand for a license. So it's quite a big difference in cost. Your finite element data can be assigned to either your nodes at the edge of your cells here, or the face of the cell. Your finite element handles diagonal flow better than finite difference, and more data density can be achieved using relatively lower cell numbers. With finite difference, we assign the data to the center of the cell only, and flow can only take place at right angles to the cell. So you can't have diagonal flow. It would have to go from there to there to there to there. And if you want to get higher resolution, you need to refine your grid further. So you would need more cells to get a higher resolution. Any questions on the types of models so far? Anybody agree or disagree with what I've said about the types of models? Did I miss one? Okay, so I'm going to carry on then. Anybody have any suggestions about where we can apply a model? If I say you're going to model something, where do you see an application for a numerical analytical model?
I think in most cases this will relate to groundwater flow or contamination.
Okay. Anybody else?
I use it in dewatering applications and to test boundary conditions.
There we go. So testing hypotheses and seeing if something's going to work. Anybody else? Yeah, we'll carry on. So why do we model? I've got a chat here. Groundwater delineation and catchment. Yep, there we go. Defining our environments. So we model the groundwater environment is full of complexities and complications. So it's difficult to define with confidence exact conditions, so exact boundaries, exact pumping rates, etc. So we need to evaluate these different conditions. And typically you can only assess your groundwater conditions accurately by installing multiple boreholes and conducting fine resolution monitoring. So you're going to have to drill on like a 50-meter grid to assess something exactly. Yeah, and even when you install these costly systems, your interpretation of the system is still somewhere where there can be an error, and your predictive qualities are limited. If you're monitoring something, you are seeing what has happened. You're not always looking forward, you're looking back. You're saying, okay, I've got a negative trend. That is interpretation, what's happened already. You're not preventing the negative trend, you're just acknowledging it. So a groundwater model allows the system to be represented in a simplified but realistic way, and allows decision makers to evaluate predictive scenarios for future planning and the execution of operations. So this is a key concept here, simplified but realistic. You always need to remember to be realistic in your models. Models also allow decision makers to evaluate environmental impacts from operations before they happen, allowing for management and mitigation measures to be put in place to avoid environmental degradation. So one of the sort of key scenarios we run often for the mines in the EIA applications is to look at your waste rock dumps or your tailings dams or pollution control dams with a liner, without a liner, and to evaluate the clay liner versus a geotextile liner versus no liner. Then you look at your plume and you say, okay, economically this makes sense. You can evaluate different scenarios like that before they happen. Because monitoring is great, but monitoring doesn't allow you to prevent it from happening. It only allows you to react to it happening. Okay, so here's the model applications that we typically encounter in consulting. Environmental licensing requirements, like I said, we can predict your dewatering cones from abstraction boreholes and your contaminant plumes that might emanate from your mining infrastructure, such as waste dumps, rehabilitated open cast workings, stockpile areas, anything like that. Project feasibility determination. Models can aid in the design process of your mining operations in terms of your pit inflows, your pit design, your stability, which is your pore pressures and slope stabilization, and the overall costing of the project. So here you can see my inflows as the mine is progressing, which has an almost direct impact on my life of mine cost, which is operational costs, and my capital costs, which is where you have to do drilling and buy pumps. So this is important to know before you start the mine. So in year 6, I need to spend almost R1 million on operating my equipment and 200,000 Rand buying my equipment. Then groundwater management system design. Where we use our models, we can effectively design a strategy for groundwater management. These strategies include your dewatering designs, groundwater monitoring designs, abstraction schedules, acid mine drainage management strategies. It's anything you can think of that's groundwater related. You can typically design a management strategy using a model. Does anybody have anything to add to those applications? Nobody. Okay, so when we select our model, the important things that you need to take into consideration is, what are my objectives? Is it a flow model? Is it a transport model? Is it simulating borehole abstraction impacts? Is it simulating a well field abstraction rates? How complicated is my question? The more complicated the question, the more complicated the model needs to be. How complicated is the groundwater environment? Is it tabular aquifer bodies where you've got one aquifer sitting in a huge block of sandstone? Is it complicated? Is it faulted? Is it overthrusted? How complicated is my groundwater environment? Is there data available? If you only have literature data, you can't really build a nice numerical model. You'd have to be limited to an analytical model. So that's important. Do you have time? Does the client want your model tomorrow? Because then you're not going to do a numerical model. You know, look at the time available. What is the client's expectations? You know, what are the confidence required in the results? Do they need something that they're going to put money into? Is it a feasibility calculation, or is it just a, do we need to do further work because this is going to have a negative impact? You know, what is your confidence? An analytical model doesn't have the same confidence necessarily as a numerical model. Now, these last two are more related to the modeler themselves. Yeah, there's no point in you applying a model if you've never worked with it before. Because the problem with modeling software is that everybody's model outputs look the same almost. So your plume and my plume will look exactly the same colors, the same everything. But you know, the model itself, if it's not built properly, nobody sees the back end. Your clients don't want to see the back end. So, you know, if you don't know the model, don't use the model until you're confident in it. And then also your experience. Modeling is a lot of intuition. Anybody that's built a model or experienced, I don't know, Armand, sorry, I'm going to pick on you here a bit, but have you, what's your sort of thinking of this in terms of a modeler's experience? What difference can you see as a client between a junior modeler and a senior modeler?
That's very, very important. Those technical insights from a more experienced modeler is really, you can put a value on that. We had a discussion actually today in the office with regards to that, where our main modeling consultant managed with very limited data and just experience of the site and experience of how to interpret these models, managed to define a very complex, movement of contamination plume. So that experience and that technical insight is very, very important when it comes to modeling.
No, that's it. And I mean, it's like you say, it's if you understand the model and what the model is doing, you can do a lot more with a little bit of data. You know, you can sort of say, no, this is not realistic. The model is trying to do this, so I'm going to JIPO on this side so that it gives a realistic output. Thanks, Armand. Okay, so that's where you choose your model. That's choosing between analytical element, numerical, anything like that. And then here's just a list of some of the software. Yeah, in terms of groundwater modeling software, we talk about data management, pre-processing, which is translating your data sets into modeling data, then your actual numerical modeling, and then your post-processing, which is where you take your block data and you translate it into a map. So your green is your open source software. You know, Windows Notepad and AclePad are good for translating data sets into the model format. And ModelMuse is a good ModFlow graphical interface from the USGS for ModFlow. Blue is where you can get a sort of free limited version. You know, with PMWin, it's a ModFlow package. You can get it where that's called PM5, and it's limited to, I think, 1 million cells or something like that. It sounds like a lot, but it isn't in modeling terms. Then FeeFlow and Spring both have sort of user trial versions, also with limitations. Post-processing, I use Global Mapper and Surfer. And then I forgot to put QGIS on here, which is also an open source GIS package you can use. Okay, so it's just a quick overview of the sort of modeler's toolkit. And then important things to remember when you're using a model. Yeah, modeling of a groundwater system is just one of the tools available to decision makers. And you should treat it as such. This is just one of the things. This is not the silver bullet. This is not the be-all and end-all. You should use your model in conjunction with as many other tools as possible to make your decisions. You know, use it in conjunction with your geophysics, your drilling, your pump testing. Don't detach them from one another. If the pump testing says something different to your model, change your model. Yeah, pump testing is pump testing. If you've done it properly, it shouldn't be that complicated. Yeah, so the model is not the be all and end all. Please, guys, don't think that it's anything more than just a tool. Some key factors to remember when applying your models. Yeah, model provides an estimate, not exact solutions. Yeah, your models, you can get millimetric confidence in some model applications, but it's still off by 5 to 10 millimeters, you know, if that's what you're looking at. The confidence of your model results are dependent on the input data volumes and quality. Multiple combinations of parameters may result in similar calibration values, but different scenario results in numerical modeling. Yeah, what that means is that if you have a tight aquifer system with a low conductivity, it'll give you a similar answer if you've got a, you know, if you fiddle with your other parameters such as storage and, you know, so you always got a, calibration is not the end of the modeling process. Yeah, you'll see it when we go through the modeling process now. Because remember, 1 + 3 + 4 + 2 is 10, but so do all of these combinations of numbers. Your model's applicability and relevance to a site problem is only as good as the user's input to the model. Your model is only as good as you make it. If you don't understand your site or the site's problem, you know, your model is going to be just a model. It's not going to be useful in your decision-making process. This is quite important because often a client doesn't really know what they need. They've just been given a directive by one of the departments. And they say, I need a model because they said so. Yeah, so you need to define what your model is trying to show so that you can make sure that your data going into the model helps to show that. And one of the sort of rules you live by with modeling is the GIGO principle. It's garbage in, garbage out. If you have bad data or limited data, your model will be bad and limited. A model is just an equation. That is all it is. It's either an analytical equation where it's x + y = z, or it's a numerical model, which is a bit more complicated. But at the end of the day, you have parameters that are put into an equation, and if the parameters are bad, the answers will be bad. Does it make sense to everybody?
Yep.
Yes.
Great. Any questions so far? No. Okay, I'm going to carry on to the modeling process. Now, this is sort of a generic process that you can follow for any kind of model. It's written for numerical models, but if you apply this for your analytical models as well, it's a good way to approach these sort of projects and applications. Obviously, you know, your analytical models, you're not going to calibrate in that, but you know, the general process you'll see is quite useful. So the modeling process is essentially a consolidation of your field data into a concise, representative conceptual model of the site, where you translate your real-world entities into mathematical entities, which can be represented in your modeling environment. The application of it's the application of mathematical equations to represent current site conditions and allow for predictive simulations to be applied at a site. So you're going to represent your current conditions and then forward predict what might happen if you drill that borehole, sink that mine shaft, etc. Some of the guidelines that we use is the ASTM 2010 standard guide for application of a groundwater flow model to a site-specific problem, and then the Australian National Groundwater Modelling Guidelines of 2012. Yeah, I know the ASTM has been updated, I think in 2016, but in terms of groundwater modeling guidelines, there aren't any that are really sort of accepted across the board. You know, if you guys have come across any during your studies or been recommended any, you know, please share with the group. But these are the two main ones that I sort of go by. Okay, groundwater modeling is an iterative process where your steps overlap to allow the project objective to be met. Yeah, when you start modeling and you see your modeling results are not making sense, you need to go back and either collect more data or reconceptualize your system. There's nothing wrong with doing that. Yeah, the model is not, like I said, it's not the be all and end all. If you see something strange happening in the model, go and query your data sets. Yeah, so the steps, there's about 11 steps that you go through. The first one and the most important one is to define your modeling objectives. Then it's to collect and interpret your data, develop your conceptual model, select your code, select the model that you're going to use. Is it analytical, finite element, finite difference, etc. Then you go to address your data gaps. If there's anything standing out, like critical data that's missing from your model, you ask your client if you can go back to site and collect it, or if you can add scope to your project. They don't often allow you to do that, but yeah, if you need to, you must ask. Then you go to pre-processing of your data, constructing your model, calibrating and analyzing the sensitivity of your model, and then verification, validation, scenario modeling, and then finally your uncertainty analysis. So we'll go through each of these step by step. Okay, so before you model, you need to define the objectives. So why are we modeling? What are we trying to see with the modeling? These study objectives should include the information that you need to get out of this model. So for example, do I need to look at what the inflows to the mine workings are going to be? What's my well field performance going to be, etc. Thanks for sharing that link, Antonio. Okay, other consideration, what time frame should the model include? Is it for the entire life of mine? Is it from exploration to post-closure? Is it for the lifespan of my well field, which could be 15 to 20 years? Operational phase only, where you're excluding closure and post-closure? How long does my model need to run for? Is it a flow model, transport model, or is it a combination of both? What is the purpose? That comes back to your confidence in the results. Is it for a license application? Is it for a feasibility study? Or is it operational, where they're designing pit slopes, etc., from your modeling results? Like I said, what confidence is required? These two are sort of interlinked. And then what is the modeling time frame? This is also important because you can't build a decent model in a week. You can build something, but you do need quite a lot of time to build a decent numerical model. Typically it's between 4 and 12 weeks, depending on the complexity. Analytical modeling you can do in a day or two, depending on how readily available the data sets are. So this is quite an important one when choosing your modeling software. Okay, and this is just an example of how your confidence in results impacts your costs and your time frames. Just sort of put together a rough scope of work for like a desktop level assessment where you can get your confidence up to about 55%. Then your EIA levels going up to about 70%. And then feasibility or design level assessments where you go 80 to 95% confidence. You can see it increases time and cost associated. Okay, modeling process continued. We collect and interpret our data. The input data should be collected from the site and consolidated into a central database for interpretation. So this will include your desktop review, your data analysis, and all those kind of things. Data to be collected includes your topographic, climate, and surface water data. Groundwater reports available for the site. That's your drilling and pump testing data that's been done before any previous investigations, if there are, the client has been around for a while. Groundwater level and quality monitoring data sets. Geological, geophysical, and geotechnical data sets, if there are any. Construction and mining plans, or mining plans rather. That's your past, current, and future plans. Geochemical data, if available and applicable. Data from your surrounding operations. Yeah, is there a mine next door or a construction site next door that could impact on your model? And then if there's any previous modeling exercises, you need to go through these. Conceptual model, we need to describe all the different environments and how they interact with one another. Your conceptual model includes both your regional and site-specific data per environment, which you then consolidate into a central data set where you simplify and apply your concepts to represent it in the modeling environment. Yeah, this we've gone through in quite a bit of detail in the previous session, so I'm just going to skim over it for now. The next step is your code selection. Yeah, when you're doing your code selection, you need to determine the code which is best suited to represent and simulate the hydrogeological system that you've described in your conceptual model, and also your model objectives. Yeah. The selection of the code is dependent on the modeler's experience with a code or a solution. Yeah, again, if you don't understand the thing, rather don't sell it. Don't try to do it if you're on a project. Yeah, learn it on your own time and get a bit of experience in it. The time constraints of the modeling exercise, and then your budget constraints. That's for you as the modeler and of the modeling exercise. If you can't afford to buy a fee flow license, don't sell fee flow models. You know, simple as that. And then also, if your client only wants to spend a week's worth of professional time, then you can only do a week's worth of work. Yeah, based on my experience, the major difference in your model confidence is more dependent on the conceptual model and the available data than the code selected. Yeah, if you've conceptualized your system properly and you've interpreted your data properly, your modeling code makes very little difference to the actual outcomes. If you can understand your system and present it properly, the model only adds to your initial conclusions. If you have a bad conceptual model, it doesn't matter what model you use, it's going to be bad. Okay, and your gap analysis. This is the way you identify any data gaps that impact on the overall confidence of the model. And if you need to, you go ask for additional fieldwork or additional data sets from the clients. Yeah, this can be a major cost to the project. So you have to look at it carefully and say, if I do this, is it going to add tremendous amounts of confidence to my model? Or is it just a nice to have? Yeah, so always be aware of that. Is it just a nice to have and it'll add maybe 5%, or is it going to take it from a desktop level up to a feasibility level? And pre-processing, that's where you take the data collected from the site and you translate it into a modeling format. Yeah, this includes your time series water level and water chemistry data. You need to translate into your observation files for calibration in numerical models. Translating your geological models and your 3D pit shells into a usable format for your model. The delineation of your aquifer parameter zones. Yeah, where is my high conductivity zone versus low conductivity versus recharge zones, etc. Then determining your parameter statistics to provide realistic ranges to be used in your calibration. So that's to say where I've got, let's say for example, I've got sandstone. I've got a sandstone unit. I must look at all of the available parameters and say, for this kind of sandstone in this region, transmissivity varies between 5 and 20. So when I'm calibrating and I get a calibration result where I set my transmissivity as 0.5, that's not realistic. It's calibrated, but it's not realistic. Does that make sense?
Yes.
Great. Okay, then you have to determine your preliminary model extents. how big is my model going to be? Is it going to be 50 kilometers by 50 kilometers or 500 meters by 500 meters? And then also your thickness. If I am mining to a depth of 100 meters, my model needs to be at least 100 meters thick. If I'm digging a hole down to 15 meters, it needs to be at least 15 meters thick. Okay, then we go into constructing our numerical models. This is more limited to numerical models. So this is where we physically translate the natural real-world entities into our mathematical entities. So that's our cells or our polygons. Yeah, the construction process has the fundamental concepts of dimensionality, discretization, boundary conditions, initial conditions, and then your hydraulic properties, which is your sort of initial aquifer parameters. And during your model construction, you must remember the trade-off between accuracy of the model and your computational time. For example, a more refined model will take longer to run and may result in you missing your deadline. Yeah, I've run models where we used such fine grid cells over so many different layers. It would take about 26 hours for the models to run. So every time we had to update the model, it would take 26 hours per scenario because you couldn't run multiple scenarios on the same computer. But the results were accurate. Yeah, but you don't always need that kind of accuracy. You know, for example, in this model, the grid cell, the smallest grid cells were 25 meters. I had 3 layers. I achieved a root mean square error of 3. And I had 6 conductivity zones. And it took 35 minutes to run for the entire life of mine. And taking the same model boundary, yeah, we ran this one with the minimum cell size of 10 meters, 27 layers. I got a root mean square error of 4.9, which was worse than the simple model. I had 15 conductivity zones, and it took me 4.5 hours to run the model. So you see, it's not always better to have a more refined model. If you don't need it, don't do it. Does that make sense to everybody so far with the construction and your selections and that?
Definitely.
Great. Kingiwe, you have a question?
No, I wanted to agree.
Okay, cool. Okay, so then we go on to calibration and sensitivity analysis. So when you're doing calibration, it's the process of changing your model parameters to achieve a reasonable correlation between your model results and your real-world observations. So your modeled water level for a time period should be reasonably correlated with the actual measurement that you've taken in the field. And typically we change your parameters such as recharge, transmissivity, and specific storage. And then we get a correlation between your calculated and observed heads while your parameters are within a reasonable range. So that's what I mentioned earlier in your data analysis. You need to define a reasonable range of the parameters. If you calculate recharge for your region as between 1 and 3% typically, but your model calibrates at 10%, you need to look at your data sets, see if you've missed something, or you need to go back to your model and see what parameters you need to change. Yeah, and the residual, Mandel suggests the residual the difference between your calculated and observed values should be less than 10% of the total variation of the observation data set within the model domain. So what that means is if I've got monitoring boreholes where the measured head, the highest one is 1800 meters above sea level and the lowest one is 1700, the difference between those is 100. So my residual should be less than 10. Does everybody understand that sort of concept? Okay, we'll carry on. So the calibration of the model you can determine based on a number of equations. Yeah, the sort of big one is this root mean square error. Then you've got a mean error, mean absolute error, and then the normalized root mean square. And these equations you can look at yourself. But typically with root mean square error, if you get a RMSE of less than 5, your model's all right. And when performing your calibration, it's critical to avoid over-calibration, where you refine your model parameters to such a fine point that you get 100% calibration, but none of your parameters are actually realistic. Yeah, I've seen models where they apply to a Karoo shale a transmissivity of 200. And I mean, you'll never get a shale like that. That's maybe like dolomite levels or highly fractured sandstone fault zone layers, but not big blocks of shale. So the model was calibrated on face value, but if you interrogate the model, it's absolutely not realistic. And the results were not realistic. You know, the plume was just disappearing into the horizon. So that's why you need to define your realistic ranges so that you can calibrate and vary your data set, but you don't deviate from reality. Remember, you still have a real world application for your model. If your model is not realistic, it's not going to add value in the real world. Okay, and your sensitivity analysis quantifies the uncertainty in a calibrated model by adjusting the parameters and noting the effects on the model results. So typically we change the conductivity, storage, specific yield, and the recharge values by a factor. So here's 1. This is where my model is calibrated. Then I multiply it by half, quarter, and a tenth, 1.25, 1.5, and 2. And then I see what it does to my calculated RMSE, root mean square error. You can see here, increasing most of my parameters has a minor effect on it, but decreasing my specific storage changes my results quite significantly. So what that tells me is that I need to focus on getting my specific storage right, because a change in that can change my model results drastically. Okay, and then you can do model verification or validation. If you're lucky enough to have enough data, you'll take out if you've got 10 years worth of data, monitoring data, what you'll do is you'll calibrate the model with 8 years worth of data, and you'll use the last 2 years for validation verification, if you can. Yeah, so what you do is you compare your model results to a data set which was not used in calibration. Yeah, so what I've done here is, here's my calculated inflows in the blue line, and then here's actual inflow volumes that were measured. So you can see I sort of fit in with the average observed data set. So my model is not 100% accurate, but it's within realistic range. It's not sitting up here or down there. Okay, so everybody okay up to the calibration point?
Yes, Matthew.
Yes.
Great. Because now is where we sort of start applying the model. Yeah, so one of the big things we do with a model is our scenarios. That's one of the big advantages of a model, is that we can run scenarios. And due to the associated uncertainties and non-uniqueness of a groundwater flow model, predictive scenarios are performed using a conservative approach and should be treated as a tool to aid in the decision-making process. So what we do there is, if I've got huge variations in data sets, I'll calibrate my model, but I'll also say, if my recharge is half of what it is now, like in a drought scenario, this would be the impact. If we have a huge fault zone that we can't prove, but it might be there, this would be the impact. So we choose our scenarios based on the application. And these limitations are true for all of your numerical groundwater models. Complexities of fractured rock aquifers imply that the model can only be used as a guide to determine the order of magnitude of dewatering and contaminant transport. You cannot model every single fracture. There are stochastic models that generate your fractures in like spring and that, but it's impossible to model every single one. So you'll get, if it's 100 cubes per day, it could be between 100 and 300. You've got to remember that with your model. The interpretation of model results should be based on the assumptions the model was built on, and the actual model results will vary as unknown aquifer conditions and parameters vary in the natural system. So just be aware of these things. Like I said in the beginning, a model is not a silver bullet. Okay, and then the uncertainty analysis. This is quite complicated, so I'm not going to go through it too much because we don't usually do it, or we do it and we don't. Yeah, it's complicated. Yeah, so all of these you can read through on your own time, if you guys don't mind. Just because it's something I had to quote directly from the guidelines because it's difficult to simplify without losing meaning. But what you need to think about your model uncertainty analysis is because your modeling solutions are non-linear, your uncertainty analysis should also be non-linear. So like I said, these solutions are almost always complicated and intensive computationally. So some of the methods we use is Monte Carlo analysis, general likelihood uncertainty estimation, or GLUE process, and then your maximum likelihood Bayesian model averaging. So unless you're a modeler, I wouldn't stress too much about this. Be aware of it, but don't stress too much. Until you can calibrate and run a model, don't worry too much about this section. Okay. Any questions about the modeling process? Everybody comfortable with that? So you understand how you go from your objectives down to your uncertainty analysis and calibration and all those things. Great. Okay, so now we'll just go.
Yes. Okay.
Just going to mute you. Okay, so we're going to carry on with the modeling report compilation. This is where you sort of take your whole model and you put it into a document. And the best way, because I thought about going through what we need to include and all those kind of things, but I felt the best way to show you guys what a model report needs is to say what a reviewer would look for. So when you review a model report, these are the things that you look for. So by default, these are the things you should incorporate into your modeling report. So the modeling report should be compiled in such a way that the groundwater environment, your conceptual model, the model that you've used, and the model results are all presented in the context of the modeling objectives and in a defendable manner. So remember, you need to defend your model. You need to say why you represented this system with this modeling code, why you chose this number of layers, this grid cell size, these recharge values. So everything should be defendable. You need to, if you're doing a dewatering model, you need to say these are realistic because the recharge is realistic, the conductivities are realistic, etc. Yeah, the review methodology that I use for my model reviews is by Riley and Harbach in 2004. It's old paper, but it's still applicable. Yeah, and you can follow this during your model review. And the objective of your review is to determine the model's appropriateness for the model objectives listed in your original RFQ or your original discussion with the client. So how did your model fare against what the client wanted? If you wanted a contaminant plume and you gave him a dewatering cone, you didn't do that well. Okay, so there's several steps in the review process. We'll go through them. And the first one that we're going to look at is the appropriateness of the model code. Yeah, that's how appropriate is the code that you've selected for the site. So you have to, in your report, justify why you've chosen that particular modeling code, why it's applicable to your site, and how it meets the model objectives. Yeah, there's a number of mathematical codes, equations, solutions for solving the groundwater equations, and each of those have a unique limitation and assumption. There are crossovers, but some have more assumptions than others. When you're evaluating, what you look for, the key questions you consider is, have you stated your modeling objectives? Have you said this model is used for environmental impact assessment or dewatering strategy design? Is that in your document? Does the method, is it appropriate for the current modeling objectives? If you've chosen an analytical solution that is applicable only to unconfined sandy aquifers, meanwhile you're applying it to a granitic aquifer that's confined, then it's not applicable. The assumption of the model rules it out. And are the mathematical representations of physical processes at the site, such as your recharge, your rivers, drains for your mining operations, all those kind of things, appropriate for the current model objectives? Does your model represent the site properly in terms of what you're trying to achieve? And then the spatial discretization of the model domain. This is your model cell size, your layer thickness, all those kind of decisions that you've made. You need to defend those and state them quite clearly in your report. This is a fundamental aspect of all numerical models, is the representation of the real world by discrete volumes of materials. So that is your model cell in a finite difference, or your model element. The size of that thing, that has a volume associated with it, which is representative of a thing, a sandstone or a mine, or it's a real world thing. And the size of the model cell or the element determines the extent of variance of hydraulic properties and the stresses across the model domain. So the bigger the cell, the more generalized your data input is. So if I've got a 500 meter by 500 meter cell, I don't have a lot of variation in my data set. So the more refined you have, the more variation you can accept. Then more cells allow for a more refined representation of your hydrogeological features, such as your faults, your contact zones, etc. But you need detailed input data and more computational time to execute the model. If you have 5 boreholes spread across a 5-kilometer radius, you cannot realistically build a 10-meter grid cell size model, because your boreholes are like a kilometer apart. So you're going to be interpolating so much in between your data that it's not going to end up being too realistic, and it's just going to take super long to run. And other questions that you ask when you're reviewing, and something you need to defend in your report: are the cell size sufficiently refined to represent the important features at the site and to meet the study objectives? If you've got a fault zone, have you refined your grid cells across that fault zone? If you have a borehole that's privately owned that is a kilometer away from your tailings dam, your cell sizes can't be 1 kilometer, because then you're just going to have one result. You're not going to see an evolution of your plume. It's either going to be contaminated or not contaminated. So you do need to refine it to represent stuff properly. Are the cell sizes appropriate for representation of head distribution complexity across the model domain? Again, that's if you've got two boreholes that are 200 meters apart and there's a head difference of 5 meters, 1 meter, or 100 meters. You're going to have to refine your grid cells appropriately so that you don't end up with a huge hydraulic gradient. Then does the vertical discretization, so your layer thickness, the number of layers, adequately represent the vertical connectivity and distribution of hydrogeological units at the site relative to your study objectives? Yeah, this is something I've only ever encountered really in the Northern Cape, and maybe the Free State as well, where you've got in the Northern Cape, you've got like 300 meters of sand on top of your mining units. So you usually typically say one layer on top, which is 300 meters, then you separate it with your clay layer, and then you refine your actual aquifer at the bottom, or you just leave the top out completely. But you have to give this a bit of thought for your layering, because if you've got a complicated system, you can't use one layer. And if you've got a simple system, there's no point using multiple layers. Does this make sense in terms of your spatial discretization?
Yes.
Cool. Definitely, because you won't ever work with a homogeneous unit. There will always be heterogeneity that you have to account for.
That's it. You know, and you don't want to overcomplicate your model unnecessarily, because you are going to have multiple layers, you are going to have multiple lateral aquifer units. But if you have a simple system, keep your model simple. It's just easier to defend, it's easier to evaluate and to improve on. Again, in temporal discretization, which is your time period assigned to your stress periods and your time steps in a transient state model, which is something that was mentioned by Donies at the beginning. Your transient state model is where your stress and your input or your stress conditions change over time. So you have your mine getting deeper, your borehole getting stronger, or your abstraction getting higher rather. Those are transient conditions. So where steady state has been applied, the model needs to be evaluated in terms of the information provided by the report to justify the system is close to steady state conditions. So if you choose to run your model in steady state, you need to tell us why it's in steady state, where you have inputs equal to outputs, more or less. That you need to justify in your data interpretation and your code selection why it is in steady state and not transient state. And the key question to be answered during the evaluation process, and something you need to pay attention to in your report, is whether your time discretization is fine enough to represent the complexity and stress and head distribution over the model time. So what that means is that if you have daily variations in a certain stress, like your abstraction, if you have it where you're pumping 1,000 cubes an hour on one day, and then 10,000 the next day and 5,000 the next day, then your stress periods are sort of a day long. But if you have a consistent pumping rate over every day of every month, you can use monthly time steps or even 6 monthly where you change your recharge conditions or anything like that. If your stresses don't change daily, do not run daily stress periods. Choose your stress periods according to the stress that's being applied. Does that make sense? Does everybody follow what I mean by that? I'm going to take that as yes.
Matthew, can you actually repeat what you said there?
Okay. So when you're choosing your stress period in a numerical model, the length of your stress period should be related to the change in stresses. So let's say, for example, I'm running a model for a mine, and the mining schedule progresses in monthly blocks. So every month there's a new block added to the mining schedule. So then my stressed periods are going to be 1 month long, because in month 1, I'm going to have mining block 1. In month 2, I'm going to have mining block 1 and 2, which are stresses to the system because water is flowing into the mine and is being pumped out of the groundwater system. But if I have a mine that is only mining a block every 6 months, then I only have to do 6-month time steps, because the stresses don't change every month. They change every 6 months, assuming recharge and all of those are constant. Does that make more sense, Victor?
Definitely.
Okay. Great. Everybody else happy with that?
Yes.
Just a question on that one.
Yes.
Suppose you have got a situation where the recharge in summer is different from the recharge in the wet season or in the rainy season. Then apart from that, you have got 2 aquifer systems. You have got the one which is open underlain by the one which is confined. How do you deal with those in terms of stress periods and so on? Maybe you can help with that.
Yeah, definitely. I think I know what you're talking about. Look, in terms of the stress periods, in terms of the recharge, that would be your time steps. So then you would have a wet season stress period and a dry season stress period, where you vary your input to the system in terms of your recharge. Okay, so that's your temporal. Then in terms of your aquifers, that's going to come down to your spatial discretization. If you say your unconfined aquifer overlays the confined aquifer, you need to make sure that you've got at least 3 layers. One for the unconfined aquifer, one for the confining layer or the aquitard in between them, and then one for the confined aquifer. So that would come down to your spatial discretization.
Thank you very much. That's understood.
Great. Is this at Concola?
No, this is in Chingola.
Okay. Yeah. Now I know you guys in Zambia, you've got that sort of situation with the near and the far aquifer. Yeah, that's there's quite a lot of research done at Concola about it as well. Yeah, if you're interested, I'll send you some papers, Tony's.
That would be great, sir. Thank you.
No, awesome. I'll do that when we finished here.
It's a pleasure.
Everybody else happy up till here with what you sort of need to defend and justify in your reports?
Yes, Matthew.
Okay, so then in your report, you need to defend your boundary conditions. You know, are the boundary conditions reflected properly? Are they defended properly? Okay, your boundary condition is a mathematical entity which defines the extent of my model domain. We'll go through this a bit better with I think the mining one, because then I can show you some mining models and boundaries that we actually use. Your model boundaries could be associated with a physical or hydrological feature, such as your perennial rivers, topographic divide, etc., or artificial boundaries, which can be assigned when they're situated far away enough from the model investigation area to avoid mathematical errors during simulation. So these artificial boundaries are typically a general head boundary, which you can put far away enough so that your plume or your dewatering cone doesn't interact with it. Yeah, that you sort of thumbsuck using an analytical equation in a numerical model. You just take your, let's say, your radius of influence calculation. You say, okay, my maximum radius of influence is 5 kilometers. So I'm going to put my general head boundary at 6 kilometers. That is if you can't identify any natural boundary conditions. Yeah, another example from the Northern Cape. Yeah, it is flat. So there's no ridges. The rivers flow once every 20 years kind of thing. So there you take your general head boundaries. Okay, your key questions when we evaluate the boundary conditions is, do the boundary conditions result in an overly constrained model domain where calibration is insensitive and predictions are not realistic? So have you made your model domain too small? Have you made it where nothing affects anything else? So your model has one set of parameters, your numerical model has become an analytical model. Yeah, and then your predictions are meaningless. Then other ones are all of the external boundaries associated with a definable physical feature. So is there a river? Is there a topographic ridge? Is there a geological contact? Is there a closed fault system? Is there something definable in the real world? If not, why not? Why did you choose that a boundary without a physical feature? Are the artificial boundaries like your general heads, can you justify them? Have you defended them in your modeling report? These are all questions that you need to answer. If they are, is your mathematical representation of the physical feature appropriate? If you've got a river boundary, for example, a perennial river, there is a river package in ModFlow, and then there is a constant head package in ModFlow. You can argue if your river flows at a constant rate and a constant level that you assign it as a constant head boundary. But personally, I would prefer it as a river boundary, because then you can assign additional parameters such as your riverbed conductivity, etc. So those are the kind of considerations you need to defend. Then are there conditions where the representation of the boundary could become invalid? Is the area susceptible to drought? Can this perennial river become a non-perennial or a non-existent river in the next 10 years? If your model is for 50 years, that means something. Can these boundary conditions change? Geology does not change. If geology changes, your model's irrelevant because something else is happening. So geological boundaries don't change, your topographic boundaries don't change. But if you're using your rivers or you're using a lake or a dam or something, can this change during your model domain time period? Then is the calibration adequate for the model objectives? Where you consider your calibration level against your model objective and your accuracy requirements. If you've got a model that's calibrated to 20%, that means your model results are 20% confidence. If your model objectives are for feasibility, that's not good enough. But if it's just to get a thumbsuck idea of a dewatering volume requirement or a plume direction, not even a plume quantity, just the direction of a plume, then that's okay. But again, you have to relate everything back to the initial objectives. The key questions when we look at our models or calibration: is a conceptual model reasonable? If you've simplified a multi-layer system into a two-layer system, that's not reasonable. Does your simulated head and flow distribution mimic the important aspects of the flow system? Do the quantitative measures of head and flow differences between simulated and observed values seem reasonable compared to your model objectives? So that comes back to your root mean square error and your calibration statistics. Is it reasonable compared to your model objectives, your confidence required? Okay, so those are the big sections in your model report. Is there any questions about the modeling process and how we do it, why we do it?
I don't really have a question, but it's like sort of like a comment about the process itself. I feel like, okay, I don't know how everyone else feels, but like I feel like with the process, or maybe it's because I haven't, and yeah, I haven't done it before, like practically, and it's not just like intuitive, but I feel like the modeling process for me was like, yeah, on the surface. Literally, yeah, like you went on the surface. And I do get the fact that it's because of time, and maybe like there's a lot of things that you to get into. Like it can't just be like a 1 hour, 30 minutes presentation for like the entire modeling process. But yeah, I'm not feeling comfortable with the modeling process.
Well, look, I understand what you're saying, and the process that I went through is just the process that you apply for any kind of model that you're doing, whether it's an analytical model, whether it is a numerical model. And you know, I gave a training course a couple of years ago on ModFlow, using ModFlow, and that training course was 5 days. And the guys still didn't know how to model at the end of it. So it's a very complicated thing to condense into a sort of less than 2 week training course. So that's why I don't want to do it from my perspective for the time, and from your guys' perspective as well. I don't want to chuck something at you and then you guys get demotivated because it's confusing and it's just not getting better. You know what I mean?
Yeah, I get it. Yeah, I get it. No, I really appreciate it, Matthew. Like, I really appreciate the presentations. And I guess with the modeling process, I'll actually need to practically do it for me to understand like all the steps required and all what like I'd need to do.
Look, it's a scientific method. It's all it is it's the same as your scientific method. You define a hypothesis, you get your experiment, code selection, then you do the experiments, which is calibrating your model and running the scenarios, and then you get your results. Your results link back to your hypothesis. Yeah, so don't focus too much on the actual process. Focus on what the process is telling you. It's telling you that you've got your objectives. You need to have your data sets to do this. You need to choose an appropriate model to do it with. And then you need to relate your results back to your objectives.
Yeah, no, that part I get. Yeah. Makes sense.
Excuse me, one question, please. This conceptual model, do you do it in 3D, or how do you represent the conceptual model?
Well, that's a sort of personal preference. Sorry, Dennis. Klingiwe, are you finished?
Pardon?
You're done. Sorry.
Yeah, I'm done. Thank you, Matthew.
Okay, Dennis. Look, we covered the conceptual model in one of the previous ones, but what you do with your conceptual model, if it's a 3D system, then you represent it in 3 dimensions. Your conceptual model needs to present the core concepts of the site. Like for your case, you'd need to present it where you would have to focus on your recharge variances, your recharge zones, and then the interaction between your upper unconfined and lower confined aquifer. So you can do that with 2D sections, or you can do a 3D conceptual model. But to put your 3D stuff into a report is quite challenging sometimes.
Yes, I've understood that. Then the next question is, I think we go back to model calibration and sensitivity analysis. This model calibration, which are the major parameters can someone straight away empirically consider? Is it the recharge, or is it the water levels, or is it the hydraulic heads and things like that? Which one do you think will be fast for someone to mimic the natural activity of the groundwater?
Well, look, your big 3 are always going to be recharge, conductivity or transmissivity, and then your storage. Those are the big three. Those are the ones that you fiddle with first. Recharge, because we don't understand the recharge always at a site. You know, it can vary from one end of the site to the other's end. So we fiddle with that one. Conductivity as well, or transmissivity, because we have point sources of the data. We have boreholes that we've pump tested, so we need to interpolate between them. So there's a bit of confidence issues there. And then storage. Storage is a big one because we don't do the proper pump test usually to get an accurate storage value. So those are the big three that I would recommend you start with for calibration, just to get an idea of where you need to look.
Thank you very much. Noted, sir. Noted, sir.
Yeah, great. Armand, you had your hand up there?
Yes, I just wanted to comment on the first comment made with regards to the modeling being a little bit complex. It really is a passion. You have to be passionate about it. It takes a very, very long time to get comfortable with models, and that even if you have a master's degree, if you have 20 years experience, it doesn't really matter. It's dependent on yourself and self-study. I've worked with hydrogeologists with 20 years experience. They don't know how to build a model, even a conceptual model. I've worked with people who have 1 or 2 years experience that can build a modular model with high accuracy. So it will depend on your own study and your own motivation and how can you call it, your own guile, your own interpretation of these things, if you have a real feel for it. So it definitely relates to your passion for this and your own inherent understanding of that. And then just one question from my side is, one thing we didn't touch on is the difference between these numerical analytical models and interpolation. I've had a consultant, or there was a query regarding a landowner. He appointed his own consultant and we had to review the reports from his specialist, and they actually used interpolation, just normal groundwater level interpolation, and let's say sulfate concentrations or something like that, and they just interpolated that and they presented that as a model. For somebody like a farm owner or somebody that doesn't necessarily have a background in all of these things, he presented that now to us, for instance, and he said, this is a model that my consultant created, but it was just basic interpolation, didn't take into account any hydraulic properties. And I think that's a very important thing to distinguish if somebody does not necessarily have experience in modeling, just to know that interpolation doesn't necessarily indicate a numerical analytical model. And then also the spatial extent that they used in the study exceeded the extent of the data that they had available. So it skewed that entire interpolation even. So in terms of presenting that model, just to come back to the first query as well, you really have to have a feel and a sort of a technical adaptability in terms of your interpretation of the groundwater regime and the characteristics. So it definitely comes back to a passion.
That's the thing, Armand. And I mean, when I started modeling, I learned from a guy. He'd been modeling for about 20, 25 years. And he said it best, modeling is pain. Modeling is, I mean, I've built tons of models, and every single one will throw something different at you. You can't explain it to someone. Every single model has something that will keep you up at night. And so yeah, modeling is, and there's nothing wrong if you don't want to do modeling and you don't get it, and there's nothing wrong with it. Just because you don't do modeling as a hydrogeologist does not mean you haven't taken the next step in your career. Please don't think that at all. A lot of people think they have to do modeling, and that's not the case. I know CEOs that have 30, 40 years experience, and they don't even know how to open the modeling software, but they're a good hydrogeologist. So please don't see modeling as the pinnacle of groundwater. It is just another facet of groundwater. And then your second point, Armand, that's what I sort of mentioned in the beginning, is that all the software can spit out something that looks professional. And that's where the post-processing, where they probably did it in Surfer or something like that. And I see a lot of people do that, where they interpolate the chemistry results with no regard to groundwater gradients or source locations or anything like that. And they say, here's my model. And I didn't want to do that and mention it specifically in here, because then you get into the argument of what interpolation method you used. is a natural neighbor, nearest neighbor, Kriging, Bayesian. Yeah, you can fight about this for months, for years. You know, so yeah, I agree that interpolation is not modeling, but yeah, to get into that is like a landmine.
No, I agree. And just the one important thing that they really missed in that report in terms of interpolation, what that doesn't give you, is when you look at chemistry, it doesn't incorporate the natural attenuation, how the chemical constituents will maybe bind to the clays or something like that. It just says that the contaminants will keep on flowing and moving in that general direction or that general gradient. So yeah, that's one thing that interpolation lacks as well, is that interpretation of your hydraulic properties in your chemistry.
Yeah, that's the thing. And I mean, you can throw that report out the window and say you've called an interpolation method a model. Interpolation is not modeling at all. You know, it doesn't predict anything. It just sort of assumes the in-between points. Yeah, it doesn't go forward.
Yeah, and it looks good, so everybody thinks it's correct. So that's exactly what we did. We disputed that in terms of the interpolation is not necessarily a model.
Yeah, that's the thing. And I've seen people sell models. It's not even worth the paper it's written on, you know. It's not even an interpolation. It's sort of a sketch. You know, it's quite shocking.
Yeah, no, I agree. And like you mentioned at the beginning, having that adaptability and that experience in and confidence in your modeling capabilities, that's very, very important for a modeler.
That's the thing, and it also adds value to the client, because you're going to get models where you don't have data, like you mentioned. And if you don't have experience and you can't defend it and make something realistic, then the whole process sort of grinds to a halt, or it goes in a direction that's wrong.
No, I agree. And just one more interesting comment is, in terms of the time frame of the modeling for the industrial complex that we currently work in, it took the independent consultant more than a year to model the complex. So he started in the beginning of 2019 and it ended now, like more than a year, about a year and a half. It took him to calibrate the model for all the areas. So modeling is definitely it's a long-term commitment with a lot of aspects.
That's the thing. But you guys are nice clients, because most of my clients give me like 12 weeks maximum. You know.
Unfortunately, this is a very, very complex site, so we had to consider a lot of aspects.
No, that's the thing. It depends how committed you as a client are as well, to actually getting a worthwhile model done. So that's good that the modeler actually made you aware of it and said, listen, I can't do it in a month. I'd love to, but no. I mean, I worked on a model for about 5 years, and you know, every 6 months we updated the model. So it can go on. Just depends on the client's commitment and sort of the value that's put into the model, because what you put in is what you get out.
Yeah, exactly.
Thanks a lot. Anybody else got anything about what we went through today?
Matthew,
Hmm.
can I ask, is it advisable for one to use uncalibrated method to sort of like use it for field investigation design before one can go and collect data?
So you're saying, can you use an uncalibrated model to design your field work?
Yes, yes.
Yeah, look, I mean, it's not going to add value, because an uncalibrated model is just going to give you nonsense results. So it would be better to do a conceptual model before you do any numerical or analytical modeling. You know, your conceptual model will help you with your fieldwork design instead of your numerical or analytical model. So I would rather spend the time doing a conceptualization than running anything.
Yeah. Okay.
Okay. Yeah, because you know, with your uncalibrated models, the variation between model runs is a problem, because if you run the model once, it'll calculate ahead of 1500. You run it again, it'll be 1450. Then you run it again, it'll be 1600. So every model run has a variation. That's the problem with uncalibrated models. Anybody else?
Thank you, Matthew.
No problem, Victor.
Excuse me, Matthew, are there techniques you can use for calibration? Model calibration?
Yeah, no, definitely. I mean, you get your automated calibration such as PEST, or you know, there's Ostrich, and there's quite a few engines that do the calibration for you. My personal preference is to start with manual calibration, where I physically vary the model parameters and look at the changes, and then I sort of judge it from there if I need to increase or decrease a parameter. But yeah, there's a lot of techniques, but my personal favorite is trial and error. Just run the model, multiply your conductivity by 10, see what it does. Divide it by 100, see what it does. Get a feel for your system based on your conceptualization and fiddle accordingly. And then if you have to, then you can use PEST or the ModFlow calibration. Let me just check what it's called quickly. But each package will have its own sort of automated calibration that it would prefer. The one that is in PM-Win is PEST, and then ModFlow 2000. So those are the automated ones that you can use in PM-Win. But there's tons of them.
Thank you, sir.
Okay. The trial and error is my favorite, Donis, because you can look at your conceptual model and you can get a gut feeling and say, I think if I increase my recharge, it'll be realistic and it would make a difference. And you can test out your own theories based on your understanding of the site. You know, with the PEST and the automated ones, it just does its own thing. It does it purely mathematically. It forgets about trying to be realistic.
Okay, noted, boss, noted. Thank you very much.
Yeah, great stuff. Anyone else?
So Matthew, I just want to understand. So if like you go and change the parameters, and then like, for example, you change the conductivity and it doesn't actually change that much, and when you change the recharge, it actually has this big significant in the result. Do you sort of like go and collect data specifically for recharge because it was changing?
Well, exactly that, Victor. You know, if you've changed it during calibration within the realistic range that you've determined from your desktop review and initial data collection, then it's fine. Then you can sort of just carry on with your modeling. But if you've changed it and it's outside of the range that you determined, then you need to go do additional work to refine your data set and to get a more representative and realistic recharge value. You know, or you need to look at your calibration again and stop fiddling with recharge if you can't do that.
All right.
Does it answer the question for you, Victor, or is it a bit
Yeah.
confusing?
Yeah, it does. The thing is, like, I wanted to also understand like, how do we actually see that now when you change the recharge, like the results is like having this big significant changes, and then like, and how do we actually see that now this is where we have to decrease the uncertainty? It's a bit confusing for me.
Well, I'm just going to go back to the sensitivity analysis. This is where you sort of see your changes. So for every model run, you see here, here's my sensitivity. When I change my storage by 0.1, it increases my root mean square error from about 5.8 to about 9.2. So that's a significant degradation of my my model calibration. So it's getting worse. It's getting further from calibration. So then you have to see, okay, maybe my range is like in this 0.5 to 1.25. So that's okay. In my realistic range, based on my literature values and field values, I'm okay. It's not improving too much. It's not degrading too much. Whereas if you're getting it where as soon as you change it, if you half your parameter doubles your root mean square error, then you need to start looking for more data and refining and getting a bit more confidence in your actual input data set. So you look at your root mean square. Yeah.
Okay. Yeah. Yeah. Now I see. All right. Thanks.
Yeah. So every time you run your, yeah, sorry, Armand.
Just a comment from my side is this also ties back into your conceptual understanding of the site that you mentioned earlier. You will immediately pick up if there's something wrong with your model. If you have a very solid understanding of your scope or your site, you'll also immediately see if there's an issue.
That's the thing. If something doesn't make sense, just hang on, you know. Like to have a look at it, say, wait, the model is telling me I need a recharge of 20%, but I'm sitting in the middle of the Northern Cape where my annual rainfall is 100. Yeah, how can I have 20% recharge to groundwater? Yeah, look at your conceptual model and think about it. Just think about your site. You can be wrong. Remember, if you've made a bad decision, go back and fix it. Don't commit to it and sort of throw yourself on the grenade. Go back and change it. You've got time. You haven't submitted your report yet. You haven't looked at your results yet. So always go back. And that's why I said the process is iterative. If you have to go back to the beginning, go back to the beginning.
No, I agree with that. And just one last comment. Sorry for talking so much. Somebody mentioned earlier something with regards to how you structure your fieldwork. So your numerical model or something like that, and the calibration, you mentioned something about that. So your conceptual model, that will add to how you structure your fieldwork because you will know which data gaps to close. So you cannot go out to the field with an uncalibrated model, but if you have a conceptual model with a conceptual understanding of your approach and what you need to input into your numerical model to calibrate it, then that will structure your fieldwork. So just this conceptual model aspect that we covered or that you covered in the previous session is very, very important when it comes to numerical modeling because you have to understand that first before you even consider going to numerical or analytical modeling.
Yeah, that's it. If you don't have a basic understanding before you leave the office, you're going to run into trouble very quickly. Anybody else have anything about models, modeling processes, etc.? Nobody. Okay. I think we'll call it a day for today. Thank you very much, guys, as always, for coming and for your inputs. Armand, thank you for your input as a client. It's always nice to hear your experiences as well with us consultants. Yeah, I'm sure it adds a lot of value to everyone. And then, yeah, Klingiwe.
Yeah, no, I was just gonna agree with you. Like, and Amand has been doing the Lord's work tonight.
No, thank you. Thank you, guys. Then I will see you on the 27th for the next one.
How about the YouTube, I think, page that I require so that I can check what are the previous ones, which I didn't attend?
100%, Tony. So I'll email it to you, but have a look on LinkedIn as well. The details are there. And, you know, there is the group on LinkedIn as well for everyone. If you want to join, you know, we can chat there and share stuff and learn from each other on the LinkedIn group. It's a private group, so, you know, don't stress about sharing stuff.
I'll check it out. Thank you very much.
Great stuff, Tony. Okay, then thank you very much, guys.